I'm sure you all are quite aware that the race to space in the 50s and 60s in the last century was totally military driven. Well, not much has changed here. However, we have here the Libre Space Foundation, and they are bringing back the hacker mindset to the space ecosphere. So there is Mantos Papa Matteo and Alfredos Damkalis, and those two will now present a lecture on how to hack your way to space.
Thank you very much. So actually he spoiled half of the presentation, yeah. Okay, so I'm Manthos, and here's my colleague Freddy, and we are here to present the Libre Space Foundation and how we hacked our way to space. And when I say we, the hacker community, and not we together. So just as the X said, the old space started with the space race during the Cold War era, and started fully under the tag of defense industry and defense agencies, and is full of classified stuff, confidential, export regulations, closed technology, state secrets, even technologies that are public and data that are public in other sectors, like in aviation, like the position, the awareness of the space, positional awareness in space industry is something that is confidential. And imagine that the first people who went to space and the first people who went to moon, they fly on board intercontinental ballistic missiles built to carry warheads, nuclear warheads, through continents for a war. And the people that they were building and designing the spacecraft and the spaceships, they're the same people that building and designing war machines. So nowadays we said that we are in the Space 4 era or new space era. And the people saying that the Space 4 is the democratization of space, and they say that is the privatization of space, and that the first private rocket went to space, which is not real, because even back in the day, Saturn V, the rocket that went people to moon, is built by the private company, by Boeing. And what they said, democratization, it means that you don't have to be a fighter jet pilot in order to go to space, but you have to be a billionaire to go to space. So for us, this is not the democratization of space. So, yeah.
So we are in 2023, and the space exploration is entirely occupied by a space industry hidden behind the closed doors. Well, not entirely. There is a village of hackers that still holds out against this ecosystem, this closed ecosystem. So one of the houses of this village is hackerspace.gr, which is a hackerspace founded 13 years ago in Athens, Greece. And one of our first space projects was SatNOGS project, which is a ground station network with ground stations like this one, which is open source and open hardware design, and with components that are 3D printed, or components or parts that someone can easily find and build a station. A station that can join the SatNOGS network, a global crowdsourced network of ground stations that tracking and communicate with satellites. Currently, we have more than 400 stations around the world. And we also have a database about, which is also crowdsourced attempt to gather information about satellites, their orbits, and their frequencies that they transmit to. Also, someone in this database can upload demodulated or decoded data for the satellites. Currently, we have more than 200 million data. And we get this data and also visualize them in Grafana dashboards and help satellite teams to track their missions and find information about their missions. For example, here you can see the Bobcat 1 mission, which was a CubeSat, and I said was because now it has re-entered.
So, one day, while we're developing SatNOGS network and SatNOGS client and hacking around the hackerspace, we got a call from University of Patras, the university in southern Greece, and actually they said what the slide said. We are building a satellite. We are 6 months before delivery, and we want help to build it. So we have no idea how to build a satellite, but we said we will build the first open source satellite ever in space. So we took the challenge. We did research on the satellite, and we found out that almost nothing was ready except 3 students that were brave enough to come with us and help us and become part of this project that called UPSat and help us to build this satellite. So it was 6 months of a constant emotional roller coaster. We're going from super excitement to learning, to designing, to failing, to designing again, learning again, excitement again, and then fail again. So we build a lot of stuff. We learn a lot of stuff, and we also build the tools to build the stuff. This is a close-up picture of the antenna release mechanism of UPSat satellite. It's something that in space industry is called fancy thermal knife, but it's just it's very common in space when you want to do deployments. The easiest way to do it is the simplest way, and you just spring load the device you want to deploy. You close it down, and you held it closed by a melt line, just a string that you pass through a resistor. And when you want to do the deployment, you just pass current through the resistor. The resistor is getting heated, melts the line, and you have the deployment. So it's that simple, not any moving parts, and it works really, really well. But the problem is that when you're in space, you don't have atmosphere. So the way heat works in Earth is that you transfer heat mostly with convection. But in space, you only transfer heat with radiation. And that means that if you put the same current here in Earth as in space, you probably will evaporate your resistor. You're going to heat it up a lot more than you do in atmosphere, and the resistor will evaporate before the line melts. So we needed to build an environment to simulate the space vacuum. And we came up. So this is our vacuum simulator. It's also used for pressure simulator. So this is why it's so beefed up. It's still like this. We have tested like hundreds of parts inside it, and every time we used it, we said we should paint this F tube bottle, but we never done it. It's just a gas bottle cut in half with some really bad welds on it, and pass-through cables and a window in order to be able to see inside. And this, inside this, we did the first test and the last test of the devices that we have sent in space. This is an example of a resistor, a nichrome resistor, melting a dyneema string. I think this is, yes. And now, as you can see, that the wire is glowing, but is not evaporates, and is glowing inside vacuum. So the whole thing is just an over-engineered, low-efficient light bulb. So yes, we did the first test, and actually we burned the first resistors because we sized the resistor based on the experience in Earth, and we burned them up inside. So we need to change the sizing of the resistors to be able to operate right in space. So another thing we built is that when you build a satellite, you need to build it in a clean environment. And the reason is that there are a lot of reasons. The main reason is that when you are in vacuum again, the evaporation temperature of all materials is really, really low. So even the grease of your fingers on the satellite will evaporate and will be cover anything, like your optics, your sensors, your whatever. So you need to build it on a clean environment to avoid covering your optics with grease or the sensors and optics of other satellites that you share the ride to space. So we went out to the market, we searched for a clean glove box, and the options were super expensive laboratory equipment from Europe, or devices like glove boxes from China that ETA, like the estimate time of arrival, was like 1 month after the supposed launch of the satellite. So we built one. This is built by acrylic sheets, and has a HEPA filter, and it's designed to go up to ISO 8 cleanliness, but it measured lower than, so even better than ISO 8 cleanliness. And inside this glove box, we have built 3 satellites that went to space, 2 satellites that almost went to space, and 2 deployers of satellites. So now we're building a proper clean room, and we'll keep this just to do hard drive swaps that we have done some with no success. Yeah. So another thing that we tried to do is to follow the software style of development, the agile development, with agile development of hardware. We were doing what the software people called continuous integration. We were building mock-ups using 3D printers. We were building using lasers, or we were printing out PCBs really, really fast to do as much as to do testing, continuous testing, in order to have a really quick release cycle and be able to test stuff quickly. So those are 3D printed mock-up of the satellite in order to measure the cables, and the left one is the first engineering model of the satellite, having some of the preliminary subsystem inside it. This is the last picture of the satellite in the hackerspace, inside the glove box we have built on a holding base we have built in hackerspace, and it's the last flash of the firmware to the satellite before packed and sent to space, actually. And this is the first photo outside of the International Space Station. Our satellite is the leftmost, and this picture was taken by the astronaut on board ISS. This satellite launched from International Space Station. And the satellite deployed and transmitted normally. then failed, but yes. Actually, it actually transmitted for some days and then became a zombie satellite that was waking up and dying random times in the year. And deorbited, I think, 16 months after the deployment. So we are still continuing developing stuff. We're developing what we call ground support equipment, or GSE, for space. This is a Helmholtz, real difficult German name, Helmholtz coil cage. And this simulates, on the center of this cage, we simulate the magnetic field. You can produce whatever vector of magnetic field you want. So you put the attitude determination and control system of a satellite in the middle, and you simulate the magnetic field that this subsystem sees in orbit in order to do simulations and to simulate the maneuvers in orbit. This also is something that we are developing together with European Space Agency. Is a communication subsystem for CubeSats. It's called SatNOGS comms. It's a turnkey solution to use paired with SatNOGS network that Freddy talked about previously. It has an S-band and a UHF transceiver and also has an FPGA on board. This is under development now. Is on version 0.3 and it's going to fly probably in 3 missions in 2024 and 4 missions 2025. Let's hope, because space always has surprises. So this is a very ugly but operational stencil printer that we have built in order to do the development, because we print the PCBs outside, but we do the assembly and of the PCBs in-house. We have a manual pick and place. We use this device to apply the solder paste, and then we put the components one by one by hand. We want to buy a pick and place, automatic pick and place sometime. We'll do it. And this is the super fancy way to have to do thermal cycling. It's a reptile egg incubator. That is sold in Amazon. It uses Peltier elements to heat and cold the reptile eggs. And we modified it. We changed the controller to be able to control it and simulate the temperature we want. And we also need to add one more Peltier in order to reach lower temperatures. To do thermal cycling for space components. The thermal cycling is a procedure that you simulate the life cycle of a space component in orbit. And because in orbit you may, some components, in some orbits you have like half orbit sun, half orbit dark. You need to simulate this temperature difference between the dark and the light side. So you speed up this procedure and do it a lot of times to check, to qualify the design and also the workmanship and how well is built a component. So while we're building the egg incubator, we got another call from a friend this time, and he said that he has secured a launch, a position on the maiden flight of a rocket from a private company called Firefly, and he wanted us on board the deployer, but he has no deployer. So he asked us if we can build the deployer and take 2 positions, so to also build 2 small satellites. So those satellites called cubics, pocket cubes, are 5 by 5 by 5 centimeters, are like this big, like a Rubik's Cube. We supposedly have one here, but we forgot to bring it. Yeah, but you can come, we're in the C3 Space assembly. You can find us there. We have a mock-up of the Pocket Cube and also another device, and a lot of rotators and stuff like that. So again, 6 months. I don't know why they, they want to pressure us so much. Again, you have 6 months to build the deployer and also the satellites. Plus, we needed to send a mass simulator, like a mass dam simulator, a device that has the mass, the center of mass and moment of inertia of the actual deployer to test it on the rocket. So we started building. This is the cubic, is the pocket we built and we designed and built. This is an early, it's not so early, is the blueprint, how an exploded view of the actual satellite. As I told, it's 5 by 5 by 5 centimeters. We have already some components lying around because we developed previously a communication board for this kind of satellites. And we also started developing the deployer. The deployer is the device that you bolt on the rocket, you put the satellites inside, and then when the rocket sends the signal, you open a door and release the satellites in outer space, in orbit. So this is one of the first preliminary analysis on static load of the deployer, because in order to launch something, this is done in FreeCAD using Calculix. We only use open source tools because we think that if you want to publish something open source, the tools also need to be open source because everyone will be able to access it. So yeah, in order to send something to space, you need to prove that this is gonna sustain the loads from the launch. And this is the first thing that you do, is to do an finite element analysis to prove that what we are building is going to sustain the loads. And afterwards, you need to qualify on a real vibration table. You bolt the device on the vibration table, you shake it, and you see if it has some modal frequencies close to the modal frequencies of the rocket, and if it's going to sustain the loads. So we searched vibration table Greece, and the result was that. So we tried to find a solution again, and the closest thing we will be able to find was a laboratory in Spain that was charging 2,000 to 3,000 euros per day, plus 2 people to go there and come back, and the accommodation. And if you fail, you need to get back, redesign, and go back again. So we said that we need to go there to do the qualification, but be sure that we will pass the qualification in the first time. And we designed something to vibrate the satellites. So this is a very elaborate design. And this is the orange device is the hackerspace sander. We have a sander to sand the bottle that we never painted. So we use the sander to test the satellites. And this is in action, vibrating one of this is the first mass dummy engineering model of one of the small Pico satellites. Here is operating on the vice, and here is on slow motion. So this test was done to check if the string that holds the antenna will stay on the resistors that is tied on. And actually, it went really well, and we passed the qualification in the first time. So I think. Okay. This is the integration day. After the qualification, we took the deployer, had 6 satellites inside. 2 were our satellites, and the rest 4 were 2 Spanish entities, the friend that secured the place, and also the Radio Amateur Space Association of Spain, the AMSAT Spain. So this is the day of the final integration. We integrated all the satellites inside the deployer. We packed the deployer and we shipped it in US in order to fly. And then we waited something like almost a year, almost 1 year, because the rocket wasn't ready. We were rushing like to do everything in 6 months, and the rocket wasn't ready for 1 year and 6 months. Yeah. Okay, this is classic space, yes. And then we launched, and then this happened. Like, yay! So, boom! So one of the engines misbehaved, and during the phase called max Q, which is the maximum aerodynamic pressure on the rocket, went sideways. The front part separated completely, and then the team pressed the self-destruct button. And actually, the reason that we waited for 1 year for the rocket to be ready was the self-destruction, the self-destruction device. Yeah. So again, the call. Now from the launch provider said, can you rebuild everything in 6 months? And we said, come on, now we have the recipe, we know everything, we can do it. It's easily. The only thing that we didn't count on was the lack of components in the market. It was in the middle of COVID and middle of a ship blocked the Suez Canal, and we couldn't find anything in the market. But we made it again. On this call also, they said, by the way, we found your payload. The only thing we found from the explosion was your payload lying on a beach in California. So they said that the payload is intact, and they sent some pictures. And there was a huge part of the rocket, like a carbon fiber part of the rocket, stuck inside, and some aerodynamic magic happened, and this thing landed on a sandy beach, California, intact. The problem of the stuff we said in the beginning is that we don't have the right to publish those pictures because it's technology export. But GIMP is our friend. So the scale is wrong, but everything else is right. So they sent us the pictures and they said, we can ship the payload back to you. And this took 1 year. Because of the export regulation problems, they had problem to export from US something we have sent to them, and we have to prove them that they are not exporting state secrets. The device we have sent to them, an open source device that we have sent to them, yes. And they said that this was quick because the device was open source. They said public. They couldn't understand what open source means. So we sent some pictures from the integration and said, it's okay, the design is public, okay? And because we are allies, so took only 1 year. Yeah. And this is the damage, the only damage the device took is the broken plastic cover of the electronics of the deployer, and one brave capacitor that sacrificed his life to save the whole deployer. So we opened the deployer, and everything said were like in mint condition, intact. We opened the deployer, we removed the satellites, we removed them from the rails and put them on the side, and the deployers thought that they were in space. They deployed the antennas and start like transmitting signals. Like, I don't know how this happened, and I'm not sure. Like, the explosion became on 15 kilometers high, and this thing fell from 15 kilometers to the beach. everything intact. So we will keep one of them for like emotional purposes, I don't know. And we call the other one Lazarus and set it back in space in the first. Okay. So rebuild everything, put it back on the rocket. By the way, one of the teams couldn't able to make one of the satellites because of the lack of components. We added the mass dummy inside the deployer, and we didn't have enough components to occupy this place. We didn't have solar panels, so we just added only 2 satellites. We have the opportunity to add 4. By the way, I can tell what the satellites are doing. So those satellites, cubics, the experiment is really quick. We're using SatNOGS network to monitor satellites. And from the Doppler shift of the signal of the satellites, we can determine the orbit of the satellite. And we wanted to try some different modulations and different signal types in order to find which is the best way to do the Doppler shift calculation. So ship it, put it on the rocket, and then we got that. So this is the deployer in space now with Earth on the background. Sadly, we don't have the moment that the door opens and release the satellites because the connection with the rocket lost. But we're able to verify that the satellites were deployed. Those are the signals received from Cubic 3, one of the 2 satellites. And this is the whole mission period. Sadly, there was an error on orbit injection. So supposed to be on 300 kilometers. And orbit lifetime in this orbit is something like 3 weeks. But went in 260 kilometers, and the orbit lifetime in this orbit due to the drag, the heavy drag, is 4 days, 4 days, something like this. So we only had 3 days to do experiments and do stuff. We did it, but yeah, I think that in the next time will be better, yeah. Okay, and something else. During our travel in this space sector and space exploration, we found out that down to the engines, the people that are building the actual spacecraft and satellites and doing the actual work are people of our kind, are hackers, are engineers, we were able to found pictures like this. This is the official NASA workmanship standard guidelines showing how to do piggyback resistor and dead bug connections on a spacecraft. What is acceptable? That is acceptable to add one resistor on top of the other to fix some issues lively on a spacecraft. Not lively, but I mean like on a spacecraft that will go to moon. I don't know. So. And the most famous hack in space history is Apollo 13, that people, NASA engineers found a way for the astronauts to fix the oxygen generation system and bring them safely back to Earth using only available material on the spacecraft. So.
Yeah. So another group that is there from the early days of space race and space exploration is the radio amateurs, which with their DIY culture and their experience in radio and engineering, they managed to find their way into space. So we have an example of the Columbia University Radio Amateur Lab, which was the first published the Sputnik's recording, the Sputnik signal recording, We also have here in the photo the Oscar-1, which is the first radio amateur satellite built by radio amateurs and sent into space 2 years after Sputnik. And we also have radio amateurs in space too. Here is Douglas Willock, a radio amateur and an astronaut. And he's contacting from ISS other radio amateurs on Earth. Also, he has contacted several schools through the radio amateur in International Space Station Initiative, also known as ARIS. Also, we have another group which is called CSAT. It's a group of visual observers which, with optical equipment, track satellites. You may have seen in the night sky ISS or Starlink satellites. In a similar way, they make observations of satellites, and they can identify which satellites are, and also calculate with a very accurate way the orbit of the satellites by using the background stars, so cross-correlating with the background stars.
Another early try to unify how the people look space was the Outer Space Treaty. It was a treaty signed during the Cold War by the two sides of the Cold War under the United Nations and UNOSA. And is the first treaty that put the word mankind and space in the same sentence. And inspired by that, we created the Libre Space Manifesto. Is what we think for space exploration. We need to the space exploration needs to actually this thing that this spacecraft that we are all on board, we call Earth and orbiting the Sun, we know that has an end. And that one time in the future, we need to build a raft and get all inside and go and find another home, another spacecraft orbiting another star. And this raft needs to be for everyone, not for the rich, not for the white, not for the privileged, not for the strong. So the only way to do this is if we do the space exploration collaboratively without the profit being the reason to do it. So this is our manifesto. Those are the principles of our manifesto and the ways to achieve that, which are open source, open data, open development, and open governance. Our manifesto went in orbit on board our cubic satellites. This was one of the boards inside them, and also with a command, the satellites were able to transmit the manifesto from orbit. Also, there is a hidden secret Easter egg inside the transmissions of the satellites that is, yeah, if you want to have some special swag from Libre Space Foundation, find it out. It will be active during the days of the Congress. So yeah, go out and find it, yeah?
Yeah, just what? You can use the SatNOGS network.
Yeah, no. You don't know. Okay. And actually, that's from us. As our motto says, per liberum ad astra, with freedom to the stars. So thank you.
Space Space Exploration with Mantos Papamateo and Alfredo Stamkalis. Thank you very much. We have now some time, actually a lot of time for questions. If there are some, line up at the microphones. I'll call you from there. There's some question from the internet. First, do we have something? Yo, there is something, please.
There is one question from the internet, and how do you put the parts into the clean glove box?
Okay. Actually, the clean glove box is a positive pressure room, so you clean there and push it inside the glove box. So from every crack and every hole, the clean air goes to the dirt outside atmosphere, so you can clean them well and then put them inside. This is the way. In the next iteration, we want to also add a space between the atmosphere and the box.
Thanks. Okay. Microphone number 1, please.
Hi, my name is Yashu. Thank you for the great presentation. It was pretty amazing. And I was hoping you could maybe show a little bit more light on how do you actually obtain a space launch, because you showed the technology, the supporting technology. I saw the first launch of your satellite was carried out of international space stations. I was just wondering, how does the process look like? Did you have to get any licenses? Did you have to pay for the launch? How does the process look like? Yeah.
Okay, pretty quick. The first launch was paid by the university, easy. And the second one was free. Actually, if you are a non-profit and you are willing to risk, there are some opportunities in maiden flights that are too risky for someone to pay to add the payload. And also some last-minute calls, because there is a rocket launch and they have some spare 2 kilograms if you want to add something. So if you have something on the rack, you can maybe find a way to launch it. For us, actually, it's not really difficult to find launch opportunities. We also have some flight of opportunity aboard the maiden flight of Ariane 6 rocket. And the other ways to pay. There are nowadays space launch brokers that you go there and say, I want to launch this payload. Or if you go with the standards like CubeSats and stuff like that, it's easier. And about the license, you need to have license from the state that you are operating, and also you have to have a license for the frequency that you do to communicate from ITU.
And maybe a follow-up. I was maybe under impression you could use European Space Agency, like the ESA Academy, so you did not use that, right? It was paid by university then?
Yes. But we cooperate with a university that using the Fly Your Satellite program to launch spacecraft.
That's what I thought, okay.
Yeah.
Thanks for clarifying.
Thank you.
Okay, thanks. Microphone number 3, please.
Hi, great talk. Great talk, by the way.
Thank you.
So you said that you're developing the SatNOGS comms module. I was wondering if you already started looking into communication security for telemetry and telecommand.
Definitely, yes. Yes.
So a little follow-up. Are you working with CCSDS and those protocols? Okay.
Yes, we try to stick to the protocols. It is very difficult for the small teams to do it, and most of the times they use really weird and hackish ways to communicate.
I know.
But we try to follow the protocols and strip them down in order to be able to operate in small devices, and because we don't build a satellite that has 300 watt of power. So we try to stick to the space protocols and be interconnected. Yeah.
Thank you very much.
Thank you.
Still plenty of time for questions. Microphone number 4, please.
So first, thanks for showing the cool way you test with this low budget. And also, you showed this vibration table you built. Did you also verify, and if so, how, that these are the correct levels you have on the rocket?
No, we didn't. Actually, we verified on the table. And this is something like the paint of the bottle. Every day, every time we use it, we say we should put an accelerometer on top and try to find the levels, but who cares? We'll do it one day, we'll do it.
Thanks,
I
looking
promise.
forward to that.
Okay.
Okay. Microphone number 1, there is a queue.
Yeah, I assume there's a great difference between theoretically building a satellite and practically doing it, and assume a lot of this information is secret, so it's company secret or state secret. How did you gather all the information you needed for building a satellite that really flies?
Oh, nice question. One is requirements, yes, that sometimes you get driven from the requirements. The other one is academia, that sometimes you can find papers from universities that have already built something and you can find on papers stuff. And the other one is failure, which is the you fail and you learn. Like the first satellite failed after like 3 weeks because of a subsystem failure, that it will be easy to find out if we had the experience or the knowledge from other people's experiences. So yeah, we learned the hard way.
And this is why we go open source, to build this knowledge for everyone. And
yeah, another thing we want to do is a wiki page that's called "How Not to Build a Satellite." Yeah.
Thanks.
Thank you.
Microphone number 4, please.
Hi, what in your opinion is the cheapest, best way to go to space for people that you think should be, we should use?
It depends, but I think that the cheapest way now is to go with a pocket cube if you are able to find the license, because it's a bit difficult because they're really small, and the agencies that track the satellites.
But for people, like, do you have opinions on how?
For humans?
Yes.
Okay. Copenhagen suborbitals, I think. They are the only team that tries to do that. They try to build a crowdsourced rocket to send people in suborbital flights at start, but I assume that they're gonna go like on a proper orbit. But yes. Yes, someday. Or if you're a billionaire, yeah, you can pay a position on Blue Origin.
Okay, microphone number 1, please.
Yeah, thank you first for the great talk. I have a question regarding the manifesto you showed and about the governance and the openness. What is the way to join the Libre Space Foundation? Because last time I tried, I was told that you don't accept new members currently.
No, come on. Really?
Yes.
I think that we don't accept members. It is not a closed community. You can join our channels, and we have people that join the core team of Libre Space Foundation. I don't know. There is no formal way to join. I think that people from the community, from the SatNOGS project, or from the other project that we run, being there. And about the governance, another part is like the open development on the project, like the governance per project, and also there is the governance as organization. Yeah, I assume that you're saying about the organizational governance. Yes. Yeah, so I don't have a straight answer on that. Yeah.
Okay, microphone number 2.
Hi, like everyone said, thanks a lot. This was a really interesting talk. My question is, I assume like on the pocket cubes it's not possible, but is there any work on steering and attitude control for CubeSats? And like, is that a possibility, or is it just basically a lump of metal and electronics and it just goes whichever way it was initially deployed?
No, there are ways to do attitude determination, even on pocket cubes. On pocket cubes, mostly passive. You use magnets to orient with Earth's magnetic field. And for pocket cubes, you can use a lot of ways. There are magnetotorquers, so active magnets to steer. And you can also use flywheels and stuff like that to attitude determine. And there are also some tries nowadays to do also maneuvers with really small motors that using cold gas or ion engine or stuff like that. Yeah.
Okay, and microphone number 1.
Yasu.
Yeah.
So a challenge is developing the hardware, but what challenge do you face for the software development part?
Okay. Do you want to speak or I can take? So the thing is that critical code, yes. The problem is that you cannot press the reset. So again, CCSDS standards are having some guidelines how to build, and also we used a standard called JPL, I think, that is produced by the Jet Propulsion Laboratory of NASA for critical code, and there are some levels of criticality on the code, so we try to use this kind of, and also testing, unit testing and code testing. I'm not a developer, so yeah, but yeah, something like this. But
yeah, test.
Yes,
mostly.
Okay, do we have any questions from the internet? No. Okay, then microphone number 4, please.
Hi. So, a question. How do you envision the collaboration between Web3 and decentralized technologies with space exploration and Earth observation?
Oh.
Did you get my question?
Oh, hold on.
Okay, may try.
Silent fire alert. So basically, we're shut down for probably 10 to 15 seconds. Everything, the whole PA will come up again. Sorry for that. It has happened, I don't know, 5 to 7 times already today.
Reboot.
So, yeah. Same here. You won't hear me. So just wait a little bit, then we got it. The stream is not affected, so don't start cussing around.
I'll try again here. No.
Nope. So.
Γιατί μπήκε αυτή η φωτογραφία. Γιατί μπήκε αυτή η φωτογραφία.
Την έβαλα όταν μιλούσα για το τέτοιο.
Takes longer than usual. Hard.
To the boot.
Well.
Καλά πει.
Still troubles? Let's try. No. Nothing. What? Nothing. Damn it. Well, let's wait for another minute or so. Otherwise, we just direct the questions directly to the speakers over here. Basically the same, just without audience and people being able to listen to it.
Do you want to go on? Without mic, come on.
I'll try.
Okay.
How do you envision the collaboration between Web3 and decentralized technologies with space observation, Earth observations?
Like Web3 and collaboration between Web3 and Earth observation?
Yeah.
Yeah. Okay, I'm not sure if I have the answer, but I think that the ultimate goal is to build a network of things, like when every node is agnostic what the other node is. So if it is a space node or an Earth node or something like this, is a ground station, is a satellite, is a server, everything is the same, and work together as a mesh network, not a network, I don't know, something like this, yeah?
Okay, could you guys understand it, or can we continue like this, or bridge everywhere, or yes, no, maybe? Yes, okay, well then, let's have the non-microphone one.
My question was not so much for the satellites, but for your deployment mechanism. Have you seen...
Oh yeah, microphone is on again.
Okay.
Have you seen any kind of licensing effort or trying to replicate your designs in some other hackerspace for some other companies? Because, I mean, there's a proven to be working and proven to be sturdy solution out there now. So why not just reuse it?
I don't know why do not use that. Actually, I know that a company built a deployer that looks a lot like our deployer, but it's not our deployer. And I don't know why they didn't copy. I think that the industry has an inertia for not copying stuff, or stealing and not copying. So they try to imitate the design, but they did the same design that was over there and open, and I don't know.
But there hasn't been any effort to contact you for licensing or from some other hackerspace to build their own?
Not for the deployer. We have a lot of contacts for the satellite.
Okay.
The first satellite, we have a lot of contacts.
Yeah, thanks.
Thank you.
Okay, microphone number 2, please.
Hi, thank you. I was wondering how is liability distributed between different actors? Like who is held responsible if something breaks? Or I assume you have contracts where it says in 6 months you have to do this. What if that doesn't happen?
This is weird because you don't actually. No one has liability, and if you want to be secure, you need to be insured, and the insurance are super expensive. So we don't care. We build cheap stuff, so we are able to launch it, rebuild it, and rebuild it again. And for big satellites, there are huge contracts with liabilities and insurances. Like I'm sure that this is a thing for big satellites, but for small satellites, there are nowadays some companies that they can insure you. The first time we tried to insure something, they had no idea. They talked to us about millions of. They asked the price of the satellite, and said that we said that is something like 500 or 1,000 euros, and they said you did something wrong, add some zeros and come back again. So yes, and also there is a liability against the state if you launch something that is not certified or broadcasting in wrong frequencies. But again, because this is international law, is not clear, because you need to have a state sue another state. That is not valid. This is international law. It's something that we all hope to be real, stuff like that, yeah. Okay.
All right, now to microphone number 1 again.
So I just want to wonder if some of your work, open source work, is used by commercial companies in the industry, like, I don't know, Blue Origin, SpaceX?
Actually, we don't know.
Because it would be interesting to know if you get ahead and your work is valued in that space.
Yeah, actually, we don't know. We know that we have some contacts from companies and state actors that they are looking on it, and they examine it, and one of them is a military company from another country, a big country, and they study this because they start to understand, and now with the thing with components, the lack of components, they start understanding the power of open source and power of having something that is really yours, because they, like US, outsource all the processor manufacturing in a third country, and they realize that they don't have any foundries in their country, and they don't own any technology in this kind of area. So I think that they now understand, even the heavy moving, slow moving space industries start to understand that the way that open source software won, probably maybe this is the way to go for hardware also. So I think that there is a movement towards this direction, but I don't have any clear that this company used our subsystem to build something. I don't have something like this.
Okay, thank you.
All right, last question, again, microphone 1.
Yeah, I have one question with respect to your knowledge management. So, I mean, you're now here since, 2014, I think. And you've built some really interesting stuff with respect to your test equipment. So how do you transfer your knowledge you have about the test equipment and all that stuff you have built up there to the next generation? I mean, people come and go. You need to do engineering changes from time to time. So how do you manage that internally to get that to the next generation of students?
Documentation is the only answer. There is not other answer than documentation. And for first satellite, actually, we didn't document anything, and this is a hell. But the thing that we changed on the next satellites and the next build we are doing is documentation. We try to document everything well, and try to make guides and very nice visual guides for even for manufacturing, because this is also knowledge. How to manufacture a board, what glue are you able to use to glue these two parts together.
And you put it also on your open source websites? Huh?
Yeah, you can access them on the GitLab repositories.
Okay.
Yeah.
Okay. Thanks, Manthos and
Thank you.
Fredos, again for this really nice and entertaining talk.
Thank you.
And let's say goodbye to you with a small, big applause, whoever is left. Thanks.
Thank you.